Okay, so now we're going to start with the most complex model that describes the relationship between our concentration, which is our independent variable here, and how it determines what the effect will be, which is our dependent variable. So we have our concentration. As it increases, how is it going to determine the effect? Okay, so this is arranged in the proper form for our brains to understand that concentration determines effect and not the other way around. Now, this form should look extremely familiar to you. Let me just give you a clue. Vmax times concentration all over Km plus concentration. So this is the exact same format as the Michaelis-Menten. I told you, if you know one concept, we keep repeating the same concepts, don't we? So our Vmax, or our capacity of the system, is going to be analogous here to Emax. How many sites do we have available for our drug to bind to cause effect? So what's the maximal effect? Emax is the maximal response. So it's the capacity of our system. And also then we have Km. Km is the concentration where we're at half Vmax. And C50 here is the plasma concentration when we've reached half our maximal response. So it's the same exact thing. So this is our affinity, isn't it? The lower the C50, the higher the affinity between the drug and that receptor. So if we have two drugs that are competing for that receptor site, which one's going to win? Well, the one with the lower C50, right? So capacity and affinity, just like always, and we have our concentration as our independent variable, and E is our dependent variable. So the only thing that's kind of odd in this model, and it's what makes it the most complex model, is this slope factor, which is the a log or an exponent that has been added to fit the data. The slope factor is used to fit data to this model, and it's what makes it the most complex model. So I will show you a slide of what you have seen before in an earlier slide that showed the relationship and the effect of this slope factor we call gamma. So gamma here is that slope factor, and if we look at our model, the effect is equal to Emax times our concentration raised to the gamma all over C50, I almost wrote Km, raised to the gamma, plus C raised to the gamma. I fixed this so that we had the same Emax. So the Emax is always going to be 100%. So here is our Emax. That's the maximal response we can see is 100. And I fixed our C50. So where's the C50? Well, at the effect of 50%, our concentration here is 0.1 milligrams per liter. So I fixed the C50 to be 0.1 milligrams per liter. And then I put in all different concentrations and different gammas to get our effect. So the only thing I varied was the gamma. So I did a gamma of 3, a gamma of 1, and a gamma of 0.3. So let's do our 0.3. So first of all, I should go back. Since the C50s are all the same, that means they're all the same potency. potency is determined by C50. So since they all have the same C50, they are equal in potency. There's no difference in potency. What does change is how quickly, as we change the concentration, how quickly the effect changes. So let's go back and look at each of these individually. Let's start at gamma equals 1 first, because that's kind of our middle of the road guy. So our gamma equals 1. So that's our pink one here. So as we increase our concentration here, we go up gradually. We see an increase in our effect, pretty steep, and then it starts to slow, doesn't it? Even though we keep increasing our concentration, we're not seeing as much of an increase in our effect. So we get to a flatter portion of our curve where we don't see the effect increase very much, even though we're continuing to increase the concentration. So this curve fits a gamma of 1. If we make our gamma larger, so we go to a gamma of 3, what do we see different? Well, they have the same C50, so they have the same potency, but as we increase the concentration, we see that the effect increases very rapidly to 100%, really by here, and almost 100% here. So we go from no effect to pretty much 100% effect between a concentration of, like maybe 0.01 to maybe 0.3, and I'm just guessing this, milligrams per liter. We go from 0 effect all the way to 100 effect in a very small concentration range, right? That's 0.03, not 3, but 0.03. So this is the effect of gamma. As we increase our gamma, we have more of what we call an on-off effect. What that means is we go from no effect to total all the way up to 100% with very little change in concentration. And the same thing, if we came this way, as our concentration drops, we're going to go from going full blast to nothing in just a very short amount of time. So this is called an on-off effect. This can be kind of dangerous because you can't just carefully turn up the concentration and see what happens, because you're going to go from nothing to total in a very small concentration range. So the higher the gamma, the more of this on-off effect you will see. So let's compare that then to our smaller gamma. So here we have a gamma of 0.3. It's our lowest gamma here. What we see with this is we see an increase in effect as we increase the concentration, and then we see a real slowdown, right? And as we're increasing the concentration, we see very little increase in our effect. And in fact, we're not going to see 100% until like maybe a mile down the road that way, right? So it's a very slow increase in effect, even though we're increasing the concentration pretty rapidly. So, well, I shouldn't say rapidly, but as we increase the concentration, we see very little change in effect. It's a flat curve. So it's the opposite of on-off. It's a very gradual change in effect as we increase the concentration. So the lower the gamma, the more slow we see that change in effect as with changes in concentration. Okay, so that's the sigmoid emax model. Next we're going to talk about the emax model, where we don't have to worry about changes in gamma. The gamma will be 1. So we'll move on in the next video.